Alright, exercise 21. This one's a little tricky and it has quite a bit of notation, but it's not too bad. So, first, what do we want to do? We want to define, let's see here, we've got alpha in use, so let's define beta from x cross y star to x star cross y star by beta of h is the pair fg, where fx is given by h of x0 and gy is given by h of 0y. Then the norm of f and the norm of g are both less than or equal to h. And that should be easy to see, right? The norm of f, norm of h0. Right, because see here, h is on x cross y star. So right, so f of x, the norm of f of x is just going to be the supremum over all x of this absolute value. And so for each of those, you obtain this equality here with h of x and 0, but the absolute value of h is given by taking the supremum, where you're allowed to vary this other variable here as well. And so you could possibly increase the value by varying this, and so that's why you get this inequality. So let h be any element in x cross y. Actually cross that. Let it be such that the norm of h equals 1. So it's not just any element. Then since I'm not going to write that, then the norm of beta h is just equal to the norm of f comma g. Sure, I'll write that out. F comma g, which by definition is equal to f plus g, which is less than or equal to 2 times the norm of h, but norm of h is 1, so it's just less than or equal to 2. So norm of b is finite. So what we want to do is we want to show that alpha is an isomorphism. So we want to show that beta is its inverse. Next, alpha beta of h of, right, so alpha you give it an f and a g and then an x and a y. So the fg pair is going to be given by beta h. And then this of xy is equal to alpha of fx gy, and that's equal to, no, shouldn't write it like that, fg xy equals fx plus gy. We know that this is equal to h of x0 plus g of 0y. That doesn't look right. No, it's h of 0y. And by linearity, this is h of xy. Oh, is it obvious that these are linear? If you look at alpha, it's kind of obvious because you put scalars. So where does alpha go from? X star. So, right. So yeah, if you put a linear combination, Right, if you put a linear combination in for the f's, the linear combination will come out here, and so that's fine. Same thing with the g's. And so you can see visually that alpha is linear, and as for beta, beta gives you just a pair of h and this, and then you plug in a linear combination, and you use the fact that, where do f live? F and g live in x star and y star, and so they're linear, and so you use their linearity and it gets them. It would probably be best to write that out fully, but it's not too difficult. You just kind of do the straightforward thing. You inherit it from the linearity of the other things. So this, you plug in an h and an xy, and you get hxy. And beta at alpha fg xy equals right, alpha fg xy. Yeah, now this becomes f of xg of y, and this is equal to, what is this? This becomes just the pair f of x equals h. So we want to evaluate this at, so this is f of x, where f of x equals h of x0. So this is f of x plus g of 0. And then likewise, this gives us f of 0 plus g of y. But these are linear, and so you plug in 0, you get a 0. Right? Yeah. Right, because scalars. And 0 is a scalar. So this is f of x, g of y, and that is fg evaluated at x, y. So you plug in the fg, you get the, so it doesn't do anything. So hence alpha is an isomorphism because it has inverse beta. Now, I think you only need one of these directions, but I mean, that's like an algebra thing, so I forget how it works, but whatever. Here, the two things are pretty easy to show, so you just do it, and so it's these are the inverses. So now we want isometricness. So next, f plus g are zeros. So for all f in x star and g in y star, we have norm of f plus norm of g, should probably start a new line, equals, no, I don't need to, equals the supremum over all x, norm less than or equal to 1 of fx, plus the supremum over all norm y, less than or equal to 1 g, no, that's just 1, right, because this puts us into the scalar field, and in the scalar field we use norms. But then, what is this? This is just, we can combine this into, this is a supremum of the sum where we take all x and y less than or equal to 1. But if we look at the norm is defined so that this is just precisely norm xy less than or equal to 1, f of x plus g of y equals, and then star, because we're going to come back to it, this is sup, same set, x, y, norm less than or equal to 1. Now we bring them both inside the same norm, which should kind of startle you, and that's why I put the star there, because we have to readdress that. And this is precisely norm of f plus g. So if this this will confirm that it's an isometry because the norm of f plus g will be the same of the norm of the things that the pair that you put in. And so, right, because this is just alpha, this is the norm of alpha fg. And this is the norm of fg. So there you go. And then this is where star holds because, well, you know the one direction is easy. Obviously, this is less than or equal to this because of the triangle inequality. But we want to know that you can attain this norm fx plus norm gy by considering values of this form, which you don't know necessarily. So star holds because norm x equals, what is this? The sine of fx, x. Is that right? Maybe this should just be the sine of x. What was I writing here? So if you take the sine of x and you multiply it by x, you should get norm of x. Yeah. So the norm of fx equals the sine of fx times fx, but f is linear, and so you can bring this scalar inside. So fx plus gy can attain the supremum for all xy here. I'm going to call this fx1 gy1 can attain norm fx2 plus gy2, because what you can do is you can take your value x here and multiply it by, if you multiply it by its sine, then you basically add in its absolute value, and so you can get to this sum here. So that should work. Am I completely convinced of that? Yeah, because the sine of x is just something of norm 1. Why doesn't this... And why doesn't this... So the one thing that I'm getting tripped up on here... Anyways, so let's just take this for granted, and then hence, what does that tell us? This tells us that alpha is an isometry, because this is the norm of alpha f, and this is the norm of f. No, this is the norm of alpha fg. No. Right, this is the norm of the... This is the norm of the pair f here. Let's write this out. Fg. This is alpha fg. Alright, and so alpha is an isometry. And there we go.